Welcome to Demystifying Python's Global Interpreter Lock. The Global Interpreter Lock, or GIL, is often misunderstood. It fundamentally changes how Python software works with modern, multi-core computer processors. Think of it this way. Imagine 8 master chefs sharing a single knife. Even with the manpower to chop 8 carrots, 7 chefs stand around waiting for the one active chef to finish. The GIL acts as this single knife policy for your processor. The root cause of the GIL is the need for thread-safe memory management. Python uses reference counting to manage memory. When an object's reference count drops to 0, Python deletes it from RAM. This process requires absolute precision to prevent system crashes. The threat lies in a race condition. If 2 threads modify the same reference count simultaneously, the count becomes corrupted. This catastrophe could cause Python to delete a variable while a core is still using it, leading to a fatal segmentation fault. CPython's solution is the Global Interpreter Lock, a software-level mutex. Instituted to prevent immediate crashes, the GIL dictates that only one thread can execute Python bytecode at any given time, regardless of how many CPU cores you possess. This creates the illusion of multi-threading. Writing a Python script that spawns 4 threads might imply a 4 times speed increase on a quad-core processor. However, physical reality dictates a very different execution path. In the anatomy of a CPU bottleneck, the OS assigns 4 threads to 4 physical cores. The Python virtual machine grants the GIL to thread A, and it begins execution on core 1. Cores 2, 3, and 4 sit idle because the remaining threads are blocked. After a few milliseconds, Python forces thread A to drop the lock. Thread B snatches the GIL and calculates on core 2, while thread A freezes. The result is the CPU rapidly juggling the lock between cores, utilizing only 1 core's worth of total processing power. The GIL only bottlenecks CPU-bound tasks. If your program relies on heavy mathematical calculations, the GIL restricts performance. However, if your program is primarily input/output bound, the GIL is perfectly fine. In I/O-bound tasks, sleeping threads voluntarily drop the lock. For example, when downloading web pages, the CPU is faster than the internet. Thread A goes to sleep waiting for data and drops the GIL. Thread B picks it up to request the next page. The network is the bottleneck, not the CPU. For heavy hardware utilization in fields like data science, developers bypass the GIL using architectural workarounds. This allows all CPU cores to fire at 100% simultaneously. Workaround 1 is spawning entirely new processes using the multiprocessing module. Instead of threads sharing a single memory heap and lock, separate processes have their own memory heaps and locks. This allows cores to run at 100% capacity simultaneously, but processes consume significantly more RAM than threads. Workaround 2 is offloading to C extensions. Libraries like NumPy and Pandas are written in C. When multiplying large matrices, the Python script hands the data to the underlying C code, and Python releases the GIL completely. The C code utilizes all available CPU cores. The future of Python is free threading. Newer versions of CPython, starting around 3.13, are rolling out free threading. By utilizing advanced memory locks, the GIL is finally becoming optional, unlocking true multi-threading capabilities in pure Python.